Today, actually, it's a bit of a special stream because we have some guests which are not our usual, computer graphics, shader toy crowd. We have some people from the Harvard University, from the Graduate School of Design, or GSD, as they call it. So I have a friend there, Professor Jose Luis Garcia, and his students are learning how to generate, I believe, mathematical structures for architecture based on like nerves and polygons and these kind of primitives. So he thought it would be a great idea for them to have a look to how we do things in this other side of the fence in the game development community, but especially those who are doing procedural content in shader toy and systems like that, like Demoscene and other communities of people who are creating procedural content with maths, but without necessarily using polygons and traditional computer graphics tools. So welcome to them. I would say actually for them as an introduction that what we are going to be doing today is different to what they usually do, in that what they do, I think I would call it explicit proceduralism, where you define rules in the computer that tell the computer where to place different elements in space, how to place those elements. Like you have triangles or control points of a Bezier surface or an herb, and you say, okay, put this point here in these coordinates, put this other point here, and those 2 points will connect with a line, and maybe a third point connects as a triangle, or a fourth point connects as a patch or something. But basically the rules and the procedural techniques define step by step where to place elements. While what we do here, what we are going to be doing today, is still using mathematics and still use procedural techniques and programming, but not necessarily to place elements, but to define volumes in an implicit way. So that's why I was saying explicit versus implicit. So what we are going to be doing is defining formulas, like the formula of a sphere, the formula of a box, and then let the computer guess where those elements are in space based on that more abstract representation of the geometry. So once we have some geometry going, we will see some of the techniques I use to make the pictures more pretty and beautiful and realistic, which, I keep calling it making them pretty, but it's not only about making them look beautiful in terms of colors and composition, but also to improve the readability, or how easily your eyes understand what the scene is, how it is composed, and what are the elements in the scene. So depending how you place your shadows, your lights, your rim lights, your highlights, you can sometimes either make the image more confusing and busy because there's just too much detail, or you can make it cleaner and easier to read to the eye, which becomes important when you're making a film and a shot is 5 seconds long and the audience just came from another shot, there is a cut, and you are presented with a new image and you have like 2 seconds, 1 second perhaps, to quickly understand what you are seeing without having to spend 10 seconds analyzing everything and making a mental picture of what you are seeing. It should be immediate and easy. And in the case of a movie where there is a story point and probably a character, the lighting would also be helping you guide your attention to that one character or whatever. But we don't have characters here. We are going to do very minimal things, but we are going to be playing with lighting to help read the shapes and the objects in the scene. Okay, let's go. So what we are going to be doing today is, let me show you, is this little guy here. I hope you can see this. This is a Greek temple. Well, it is not. Like, I have no idea what a real Greek temple looks like. Actually, there was someone from Greece in the chat, Dmitry, was it? So apologies, Dmitry. I don't know how a Greek temple looks like. I've never been there. My parents have a few times, but I haven't. So I don't know if the proportions are correct. Probably they are not. But it's something inspired by a Greek temple. That's what a Greek temple looks like in my mind. So for those at Harvard, what you are seeing here, this picture here, which I'm gonna stop playing, but this image here is made just with maths. There are no polygons, there are no 3D models, there is no rendering software, there is no, Mayas or Photoshops or even processing. All that we have is this code here on the right side. And these lines of code, of which we have how many? We have 600 something. Those 600 lines are implementing different formulas and equations which combined together give us the shape of the Greek temple and the background terrain and the ocean and the little clouds and even the lighting and the composition. It's made through those equations and formulas. What you are seeing here is Shader Toy. So this is a website that I wrote with my friend Paul Jeremias. And this is basically a community where it's like a bit of like YouTube, basically, where actually let me show it to you. If I go here, where is my OBS? Here. So what you are seeing here is the main landing page of Shader Toy, where you can browse for different mathematical creations, which usually are pretty amazing. And I have an account, of course, and I'm using the website not only to share my mathematical creations, but to actually make them as well, to create. So this is a live coding environment, much like processing that I know you guys were using, where you type things here on the right side of the screen, where the text goes, and then I compile, and the left side of the image responds to the code and creates an image accordingly. So without going into much detail for now, because I want to jump straight to the coding and the modeling, but just to give you a very, very quick sense of how things work. Basically, this program on the right that says my main, it's running for every pixel of the screen. So there are 1 million pixels in the screen, or 2 million, depending on your resolution. And for every pixel, this program will run, and it will take the x and y coordinates of that pixel. Starting from 0, 0 in the bottom left corner to pixel number 800 and 450 on the right side for x and y coordinates, because the canvas in this case is 800 by 450. So for every x and y coordinate, the program runs and takes x and y, which is two numbers. It does maths on them, like adding them together, multiplying them together, doing a square root of one minus the other, something. And then those numbers that you get out of those formulas get interpreted as colors. So basically we are going to inject those numbers into the red, green, and blue channels of that pixel. And in this case, I don't have any formula, but I'm going to just inject numbers directly. So if I put 1, 0, 0, which is this triplet of numbers here, then we are telling the computer to inject full red and no green and no blue intensities in that pixel, and then we get red. If I put 0, 1, 0, then we get green, and if I put 0, 0, 1, we get 0% of red, 0% of green, 100% of blue, and then we get a blue pixel, and we can combine them. We can do cyan if we mix, blue and green. If we put a lot of red but a little bit of green, then we can kind of orange or yellow or whatever. So that's the idea. And I will do just one more thing, which is I'm going to modulate the whole color by 0 to get black, or by 0.5 to get dark brown, or 0.85 to get a bit brighter brown. The higher the values, the brighter the colors, right? So now what I could do is to take the x and y coordinates and use those to modulate the color. So if I call p the pixel coordinates, if I take the x component of the pixel and I multiply that with the base brown color that we had, because coordinates on the left side of the screen are small, we are multiplying the brown color or the orange color with small values, make them pretty much black. And as the coordinates increase to the right side of the screen, up to the point where they reach 1.0, then we will be multiplying the orange color with 1.0, which anything by one, multiplied by 1 stays the same. So we get the original orange color on the right side of the screen. So that's what we are getting. Now, I did this same explanation a few months ago with another of my live streams, and I am aware that what I'm going to do now, it's like a crazy jump in complexity, because I'm going to go from this very simple explanation to something that suddenly looks 3D. But you have to trust me that I don't want to stop on the internals of how to go from a 2D brown gradient to a 3D sphere, because that's technical. It's more programming that it is mathematics, and it is more related to how the computer works and how 3D perspective works than it is related to modeling and design and using maths to create shapes. So I'm gonna skip over that. I will do another stream. If you guys find this interesting, you can join us in the next live streams and we might touch on those topics. But for now, I'm going to go straight to this little blue sphere here, yellow sphere, which is a 3D sphere, but it is generated just in the same fashion, where for every pixel, we do some computations, and then we get a color, and if the color is blue, our eye will interpret this as the background or the sky. But if I place a color which is not blue, but kind of skin color or yellow or white, then we can make a sphere floating in the middle of the blue sky. And these maths that go from the 2D pixels of the screen to a 3D environment where you can define a 3D sphere, those equations, as you can imagine, have to do with perspective and how things which are farther away look smaller and things which are closer to a viewer look bigger. So it's kind of those equations but reversed, and there's some maths going on there. But what I want to focus today on is, and let me make the text bigger so everyone can read, is actually using maths to play and shape things. So here we are. This line of code, 160, what it says d equals length of q minus 0.9 is the one responsible for making that sphere. Actually, very quickly, if I do this, let me show you. All right, so a sphere, as you might know, is something like, x squared plus y squared plus c squared equals a radius square. That would be a sphere centered at the origin. And in this case, all the points that satisfy this equation are on the surface of a sphere. Something you can do is to take a square root in both sides of this equation, and then you would get something where you get something like that. And that still represents the same surface. The same points that satisfies this equation are on the surface of a sphere. However, this time, this quantity here, it's a distance, or it's basically the length of a given vector of coordinates x, y, and z. So basically, what we are doing is, for a point x, y, and z in a space, which has, for this vector here, which has these coordinates, we are defining, we are measuring this distance, basically. And when that distance equals r, when this equality happens, then that point is in a sphere. So we are getting, a sphere that goes through that point. So this equation here, if we isolate it and we equal it to 0, and we do something like square root of x squared plus y squared plus c squared minus r, this becomes 0. This is still the same equation than here. I just moved the r to the other side. This quantity now becomes a distance. It becomes the distance from any point in space, for example, that point here, q, to the surface of the sphere. So this quantity here, the square root, would be the distance to the origin, and then we are subtracting the radius of the sphere, such that a point that is at the surface makes this equation equal to 0. This equation is measuring distances, and this is something we can use to define geometry in space. And the algorithm that I have in ShaderToy is going to be using that distance to kind of find points in space and colorize them as blue for background or yellow for the foreground, for the sphere itself. So what you are seeing here, this line of code 160 that says length of q minus 0.9 is implementing exactly this equation I just showed you with the square root. This guy, actually, I could write it as q.x times q.x plus q.y times q.y plus q.c q dot c. So this is taking the x component of q, squaring it, taking the y component of q, squaring it, taking the c component of q, squaring it, putting all them together, making the square root, subtracting r, the radius, which is 0.9. So this can be shortened in this programming language that we are using, which is GLSL, as length. That's the length of that vector q. And 0.9 is the radius. And of course, if you know I make the radius bigger, like 1.9, then the sphere becomes bigger, and I can make it 4.9, and suddenly, our sphere is really big. There's a shadow there and a few lighting that I won't explain today, but the lighting and the shadows are made with maths as well. But for now, this is what I want to show you. Of course, if I make the radius a variable, radius equals 0.5, and now we add a sine wave to it. Let's say sine wave of, okay, that was too much. This is a time where you can play and you can start modifying the radius of the sphere, and instead of making it constant, you can add a sine wave that runs along the x-axis. And in that case, well, the radius itself goes up and down, just as the sine wave does. There are some artifacts, so we could fix them by multiplying the distance by a small number, which tricks the algorithm, which is underneath, rendering all of this to kind of fix the artifact. But you get a bit the idea that I can also multiply by c, and I can multiply by y, and add some sine waves everywhere, and suddenly I have this very funny shape that looks more like I don't know, like something organic, like something you would find on the cell of a human body or something. And so this is a very creative use of maths, in that it's not like I was sitting down and like doing equations until I found what was the perfect function that I needed to use to create an undulation of a given shape. I would just drop a sine wave there and see what it looks like. And if I don't like, I would go and change the parameters and find another sine wave that looks better. And sometimes there is this kind of creative process where there is not so much hardcore maths, but more playful and very pragmatic use of mathematics. And that way, actually, by playing like that, it's very easy to gain intuitions about things like frequency and amplitude and phase of a sine wave, for example. And sometimes we use exponentials and whatnot. So we very quickly developed intuitions about what functions to use for shaping things in a given way. That doesn't mean that sometimes we don't do actual hardcore math. Sometimes we also do integrals and we find what's the exact function that we need. But sometimes there's also a lot of playfulness like this. And the last thing I'm going to show you before going to modeling is that all of this is real time, as in, I just added time as phase, like a phase offset for the sine wave that run on the x component. And now the x component of those bumps is moving basically with time. So the longer we wait, the more the sine wave is going to be shifted in a given direction. And that makes the whole thing move. And that's great because by virtue of having everything run in real time, we can iterate very quickly. And that process of developing intuitions and finding what sine waves look good and which ones don't, we don't have to spend days trying numbers and waiting for the computer to render. We can do it live and very quickly understand which values look good. Anyway, I'm going to go back and start modeling the Greek temple. So we want to make columns. I'm going to start doing those columns that create that hold the roof in the temple. And basically, those are cylinders. We are going to start with cylinders and then we will shape them a bit. But cylinders are pretty much kind of two-dimensional spheres. They are like a circle that got extruded. So it's like you had a 3D sphere and you kind of forgot about one of the components and kept it constant, and just took the circle that makes the profile of the sphere and just extruded it. And that's very easy to do because we can take just two components of our point in space q, which is a three-dimensional point, and instead of considering x, y, and z in our equation, let me go back to the maths. So here we were using x, y, and z to represent our sphere. But now if we just use x and z and we forget y, then we are basically ignoring y, and it means that no matter how high you are in space, you are going to be creating a circle at that height in space. And because we are considering all points in space, so every height or altitude in space will run this formula, then we are going to be stacking a lot of 2D circles basically, and that makes a column. So this equation here is basically going to create a cylinder like that. It's going to be an infinite cylinder though. So actually let's try that. So if I go here and I just put the x and the y components, or x and c components, then I get an infinite cylinder. And there it is. So the problem is that we don't need an infinite cylinder because, you know, the temple is only that high. So I'm going to clip it or create kind of a plane or a cap for it. And let me copy these equations. I think I used a 6 here. There we go. So what I did now is adding 2 more lines of code. I was able to cap the cylinder. And normally there are better ways to do this. This is not how I recommend doing it. This is not as efficient as using the equation of a cylinder. And that's one of those cases where I would go in paper and compute the exact equation of a capped cylinder. But this is an approximation and runs good enough for our purposes today. So what I'm doing here, the max equation here, has 2 components to it. So first there is the max function, which takes the maximum of 2 values. You know, the max of 6 and 7, it's 7. And the max of -2 and +3, it's 3. So then we are taking the value that we had for the distance to the column, or to the infinite cylinder, and pass it through a max function with some other distance here, which I could call d2 if you want. And we are going to take the maximum of both. And the second distance, d2, is the distance to a plane. So I created a horizontal plane that goes through an altitude of 6 units. I'm using arbitrary units here. They could be meters, perhaps. And again, Dmitry can tell us how tall one of these temples is. I'm sure they are more than 6 meters. But let's say they are 6 meters. So I'm going to clamp the column at 6 meters by creating a plane, infinite plane, that is at 6 meters. And the equation of a plane, again, for an infinite plane, you know, something like that, would be as simple as what height it is. So y equals 6, for example, or -6 or something. And that's the equation we are using. So then, because we are clamping, let me draw this again, because we have a cylinder and then, well, it's an infinite cylinder, but basically I'm clamping it through a plane. We are generating this other cylinder here that is constrained to the plane. So that's what we are doing here. This is the equation, you know, p equals 6, but I equate it to 0 by passing the 6 to the other side of the equation with a negative sign, and that becomes y minus 6, and that's what I input here to create the clamping. And I'm going to also clamp it in the bottom side of the screen with another plane. I don't know if you can see the difference there at the bottom. It's no longer touching the floor. It's floating a little bit above it, and that's fine. I had to reverse the sign of y because now the plane is pointing down. The previous plane was facing up. This one is facing down, so we get caps on the cylinder that make sense to the viewer. You know, if you have the surface normals of this shape, the cylinder is facing us. All the normals on the surface are pointing outside of the cylinder. At the top cap, we want the normal to point up, and at the bottom, we want the normal to point down. So there is a reverse on the normal y direction for the caps. That's why there's a negative sign there. So, okay, let's keep modeling this a little bit. I'm gonna make them a little bit more irregular. I was looking at some pictures of real temples, and normally the base of the columns is a bit thicker than the top. So we can do that where, you know, this is the radius here, and we can make the radius non-constant, just as we did with the sine wave to create those bumps on the sphere. Now I can create a non-constant radius to shape the column. So I'm gonna add something like that, q.y. So what I did is, you know, if 0.9 was the radius, and by making it smaller, I can get the column to be thinner. Then I'm gonna subtract not a constant amount to make it thinner, but an amount that is bigger at the top. So we are gonna subtract more radius at the top to make it thinner. So I can't just take the y component of the point and subtract a given amount. So I could make it more dramatic, you know, by subtracting 0.2 or 0.1, but I found that 0.05 makes for a good shaping. And again, this is a bit of a hack, as in this cone has also a mathematical equation which describes its shape perfectly, and that equation is not this. So this is an approximation, and I have equations in ShaderToy and in my website that you can use to create the exact Sine distance field, or the exact formula for a cone that has this shape. But we are not using that here, just for the sake of having a good time, moving fast, and getting something that is approximate, because we are going to be doing so many things anyways that break the maths, that having one more mistake here doesn't really change things too much. Anyway, let's make this a little bit more pretty by, you know what, I'm going to call this thing radius, so we don't create a super long line of code. And I'm going to keep modifying the radius. I'm going to break this in steps, actually. I normally like breaking my code in steps that make sense. And by that I mean that, you know, this is the base size, and then we shape thinner at top, and now we can create more operations on top and stack operations. And this is pretty much how an artist would work in Photoshop, right? Or in any program, where you start with something basic, and by layering detail and detail, you can make the image as complex as you want and as beautiful as you want. And this is pretty much similar. We start with a simple shape, and we start adding and layering little equations. Instead of little brush strokes, we add little equations one by one, and then we get more and more detail. So I'm going to use a sine wave of, let me see, this should be Q.C, I suppose. And then let me write it, and then I will explain that. Well, actually, let me explain it right away. So I have created a quantity here that, wow, okay, you know what? Let me do it first, and then I will explain it. Okay, look at that, I already got it. So what did I do here? I modified the radius of this cylinder by an amount of 0.1. If that was just constant, the cylinder would become smaller again, but I'm modulating that carving effect, that 0.1 of carving, with a sine wave again. But instead of running the sine wave along X, I'm running the sine wave along the perimeter, or the circumference of the column. So, okay, let me draw it. Maths. There we go. So, top view of the column would be like a disk, like that, a circle. So what I'm doing is I'm measuring the angle of any point in the surface. I'm measuring that angle, alpha, here. Okay, let me make it bigger so you can see it. I'm measuring alpha. And alpha for a given point X and C is going to be the arctangent of X over C. So this is X and this is C. Actually, it's going to be C over X. Doesn't matter really. It's just an offset. But basically, we are measuring the circumference all the way from 0, you know, to pi to 2 pi, or tau, if you want to call it that way. And that measurement, that distance along the circumference, we are going to feed it in a sine wave. And as you know, as we saw earlier, the sine wave is going to do that. And then what I'm going to do is to compress the sine wave many times. I think I did compress it 16 times. So that sine wave that goes from 0 to 2 pi is suddenly going to become, 16 of those sine waves from 0 to 2 pi. And those then, through the arctangent, they get wrapped around the circumference of the sphere. So that's going to become basically a sine wave that does something like that, geometrically in space. And then I make it small, because the sine wave, as you know, goes from -1 to +1. I multiply it by 0.1, 0.1 as you saw, so that makes it smaller, and then I add it to the column. So what used to be just a column like that, suddenly it's gonna become a column like that. So that's what we are doing, basically. Let me go back here. So we have the sine wave here. I just, instead of going from -1 to 1, I always like my signals, as we call them, like all these pieces of information, to go from 0 to 1 instead. So to make something go from -1 to 1 and remap it into a 0 to 1 range, we have to multiply it by a half and add 1/2 to it as well. So that's what I'm doing here. And once I have that, then I can multiply by 0.1 and subtract it from the radius, so we can carve a bit of a shape. One thing that we often do when creating these mathematical shapes is to take a signal that, like this sine wave that we had, and change its shape and control how spiky it is, how smooth it is, how rounded it is. And that's something we can do with power functions, like x squared, x cubed, x fourth, or x to a half, which becomes a square root, or x to the -1/3 or whatever. So these powers that we use can change the shape of a function. So in this case, if we had a sine wave like this, which goes, this is 0 and this is 1, we had a sine wave that was going from 0 to 1 now, thanks to the biasing. If I square it and I make sine squared, like sine times sine, then you get something that is more like spikier, more like a comb. And that's what I want, because I want my columns, the profile of my columns, not to be like, like a smooth flower shape, but I want something that is more spiky, like that. I don't know how to draw it, but probably you get the idea. I want something spikier, so I have to square the sine wave. And that's what I did here, or what I'm about to do. I'm taking the whole thing and squaring it. And now I have something that looks better, more like I want. It's a small detail, but all the small details count in the end. And then something else we can do is to create the fake sense of bricks, having, like this column would normally not be made of a single chunk of stone. It would be made probably of smaller blocks of marble or stone or some sort of material, and they would be stacked on top of each other. So we can simulate that by taking the radius of the column again and pushing it inside and carving it, carving little, planes into it, or like little rings that happen at periodic intervals as we move vertically on the column. And another way to create periodic signals is by using a sine wave, because sine waves are periodic on their own. So it's going to be very similar, but instead of using the arctangent to measure positions along the circumference of the column, I'm going to be measuring positions vertically in the column to create those carvings periodically. And that's just the y component of the column. And you can change the frequency, and now there you can start seeing some of the let me make this bigger, some of the shaping that I'm getting. But so you can definitely see the sine wave on the profile of the column there. Maybe I can bring the camera closer. Let me quickly bring the camera slightly closer here. Okay, there we go. There we go. So sine waves, they are very periodic, but I want something that is more like straight and then very quickly curves in to simulate the gap between two blocks of stone. So I'm going to use the power function again. Instead of squaring it, I'm going to use a power that is smaller than 1. So 0.5 makes it a square root. Maybe, this I don't like. What about let me see. Should I make it positive? Yeah, but then I can subtract 0.15 again. Okay, I got it. So basically, I think I can do this. No, I'm gonna put it back to what it was. I think I got it right. So this is the problem with improvising, that I will get things right and sometimes I won't get them right. so this is the difference with and without. So what I did is to take the sine wave and pass it through a pow function with a very, very small exponent. So basically, the comb shaping that we made before is that to the extreme, where basically the sine wave is staying high and only in a very few locations goes down and very quickly, very rapidly comes back to be 1 again. So it's like a sine wave, but you push it up, the points which are at the very bottom stick to the bottom, they don't move, but as soon as something is not at the 0 level, it very quickly goes up, and basically that makes the whole shape go down very rapidly and recover very rapidly as well and stay up. And that shape is exactly what I need for the profile of the column to create those fake bricks. All right, so let me move the camera back to where it was, which I think it was 25. So now let's add more detail to this. We are going to add 2 boxes, or a box at the base of the column and another rectangle or a box at the top. And when I do that, I will take a small Q&A so we can have a bit of time to talk about other things. And I think that my stream is going to be longer than 2 hours for sure, but we'll see how long it goes. At least we will cover all the modeling that I want to cover, and then we will do lighting at the end for the brave ones who stay alive after all of this. Okay, so boxes. I don't know if I should explain this. Probably no. I'm going to skip it and go straight to the equation of a box. Let me show you the equation of a box already created for us. I don't know which equation, which size should it be. I'm going to improvise it a bit again. Okay, that's a box. Can you guys see that box there? It's a tiny one, so let me multiply that by 3. Okay, there we go, a box. The same way we had the equation of a sphere, which was the square root of x squared plus y squared plus z squared minus radius. We also have the equation of a rectangle or a box of arbitrary dimensions, and actually have a whole YouTube video just on that. If you look up for my name in this same channel that you came to see the stream, if you browse the videos, the second to last video should be one about how to create the equation of a box. And it also involves one square root and a few coordinate manipulations. Instead of being x squared and all that, there is a few max functions and a few other things that go on. But basically it's like a truncated sphere in a way. So I already encoded that function here. This is the equation of a box. I won't explain it, but it's just a couple of lines of code. It is not a lot. So basically, it's not a very expensive operation. But you can think of this like a square root of coordinates, and that creates a box. So what we have to do now is to combine the box with the column. And that's something that we can do by using the min operator. So earlier we used the max operator or the max function to clip the column. We had an infinite cylinder and we used the max to clamp it and create a top cap to it. This is similar, but instead of cutting, we are gonna combine 2 things. It's not, it's not subtractive. It's like additive or combination of things. So in that case, I take the min and the reason to use min is the way the technique or the algorithm or the equations that we are using to project all these shapes into the screen. The way that algorithm works is by measuring distances and by combining 2 distances, in this case that of the column with that of the box with a min operation. We are pleasing the algorithm. We are doing something that is compatible with that algorithm, and we ensure that that algorithm will find either the box or the column, whichever is closest to the camera. It's technical details, we could go through it another time maybe, but basically with the min function we can combine these 2 shapes. So yeah, let's go ahead and start modifying the location of this of this column. I'm gonna call a new coordinate QQ, which is gonna be just Q, and I'm gonna subtract some amount from it. Actually, I'm gonna call it I'm going to reconstruct it from scratch and just copying the values x, y, z to a new component, to a new vector. And what did I do here? Okay, yeah, 0.3. Okay, let me see, 5.3, 0.6 maybe? Yeah. And now we can make this thing smaller. And I think that will do. 1.4, I think. Okay, so we have one there. I could move it up a little bit. Something there. And now, in theory, I could create a second one. And I could put it somewhere down there, like there, let's say. So that would do. We have two rectangles that make the base on the top of the column, but one of the advantages of using mathematics, as I was saying earlier, is that you can populate huge amounts of detail and vast amounts of space without having to explode the memory of the computer. And in this case, one box was one line of code or 2 lines of code. 2 boxes now became twice as many lines of code. So that means that the complexity of the code and the memory used and the computational expense of all of these, it just doubled because we have double the amount of boxes. So that's okay, but not ideal because it's a linear cost. But there is a trick we can use with maths, which in the spirit of doing a lot of stuff in little amount of memory, a trick that we can use that avoids this linear increase of complexity. And we can use one single box to model both the top and the bottom. So this is the trick. When you are, when the algorithm is kind of rendering or evaluating the maths for the column, and the point of evaluation is kind of at the top of the column, the only of the 2 boxes that we care about is the top box, the one at the top. The one below doesn't care. It doesn't impact neither the colors, nor the shadows, nor the shape of the column. It's far enough from the top of the column that the bottom one doesn't affect in any way. And it's not just an approximation. It really doesn't affect because the other box is closest. And similarly, when we are at the bottom of the column, the top box doesn't really impact in any way. So what we could do is something like, if we are at the top of the column, or if we are above the middle point of the column, the center of mass, if we are above it, just evaluate the top box. And if we are below it, evaluate the bottom box. So we could do an if statement, if q.y bigger than 0.5 times the size of the column, then this box, otherwise the other box. That would save, but still it's not ideal because computers not always like conditional branching like that and if statements basically. But there's another trick that we can use, which is symmetry, which is using that idea that when you are in the top half space of this column, you only care about the one at the top, and when you are in the bottom, you only care the one in the bottom. So what we can do is something like, take the absolute value of y, and let me see if this will work. Okay, there we go. So look at that, it's a single line, and I got 2 boxes, even though we are only evaluating, sorry. Oh, I screw up, what are we? Here, we only have 1 box, but the QQ coordinate is different from Q in that now anything that is in the negative half space of the problem, anything that is below the center of the column, which would make for a negative y component for q dot y would be negative. Now we are passing it through the abs function, which takes the absolute value of a number, meaning -3 becomes 3. And therefore, every coordinate which was below, let's say at position -1.5, suddenly through the abs, it's equivalent as if the point was in the 1.5 coordinate of space. So basically, any evaluation that is happening below the center of mass of the column is going to be automatically be moved to the top part. So it's like we are mirroring the space. We are doing a symmetry, basically. So, well, you have a function of x, a polynomial, an exponential, a combination of things, whatever, and you replace the whole formula, the whole equation and where it says x, you do absolute value of x, suddenly the whole function gets mirrored in the negative side of the x-axis. So this is the same. We are mirroring the whole volumetric, because this is a volumetric function. It's not just a function of x like you normally graph. It's a 3D function of x, y, and z. But we are mirroring it vertically by taking the absolute value. And now what we need to do is to shift the whole problem a little bit and do something like that. Okay, these are details now. I just was shifting the mirroring point. Before, the mirroring point was 0. But that, okay, let me go back. That was, the two boxes are not exactly centered. The one above needs to go a bit up. So I can fix that by shifting the mirroring plane by 0.3 units. And then I can make the box a bit farther away from the origin, something like that. Okay, so we got that. We got a small column. Let me move the camera so you can see it in all its glory. And actually, the camera is moving very slow. Let me move it a little bit faster. There we go. So there it is, the column. And I think I'm going to take Q&A now, very quickly. Oh, someone is asking how to turn an SDF and export it like a mesh data. Is there a way to bake the results of an SDF volume to something that can be used in-game? Okay, I missed that one. But the answer is there are many answers. One is yes, you can export data of an SDF in multiple representations. You can export it as polygons. We don't have that function in ShaderToy, but we could add it, and I'm using it myself in some of my demos and things where I take the SDF and I make polygons out of it for rendering in my own engine or in a game engine, whatever. You could use marching cubes or surface nets or marching tetrahedra. There is a whole slew of techniques and algorithms that you can use. You will always, of course, lose some detail unless you go with a super high res mesh. You could think of doing something adaptive where only high curvature areas get more polygons and areas which are more flat get less polygons. But it's complicated and not so interesting, I think. Another approach is to render the SDFs directly in a game engine. There are a few folks who made a plugin for Unity, I believe, that can render SDFs directly. And I made my own for the Unreal Engine 3 years ago. Just as an experiment. I never published or pushed it too far, but it does work. Basically, you implement a ray marcher, which is the technique I'm using under the hood in ShaderToy here, to explore the SDFs and splat them into the screen. And you implement that in a shader inside Unity or Unreal. You can put like a 3D box, like a normal polygon box in the scene. And then on the shader of that box, on the material, you write the ray marcher. And there you evaluate all the SDFs. And you take the color that you get from the ray marching and you put that in the shader. And if your ray marcher doesn't find any intersection, you discard the pixel to create a transparency mask. And if you do find the intersection, you splat the color, but also you take the depth of the intersection and you write down to the depth buffer. You have to do a conversion there between a true distance, which is a square root based, to a linear distance, which is what projection matrices use when you do depth buffer based 3D rendering. That's a small conversion, just one division. And then you can composite normal polygon things with rematch things. And then you get the flexibility of both things. You have a game engine, so you can author the rest of the game and script your game as usual. And you even have shadows from all these ray match things into non-ray match things, but you still have the flexibility to do funny effects like morph and blending and distortions and weird things, which probably are what you are after when you use SDFs, because those are things that are difficult to create with polygons. Other ways to do it is to export the SDF as it is in BDV, is it? Like a bonding... Oh, what's the name? It's the open source library that DreamWorks released for volumetric data that they use for rendering clouds and other 3D effects for their movies. So you can represent SDFs and bake them into a data structure, so you don't have to reevaluate all the equations and formulas every time, but you have just the SDF baked in voxels, basically. Is there an example of the setup script available on your website? I think I have an article where I explain how to blend the depth buffer of a 3D engine with the distance to a pixel that you get in Array Marcher. I have that. That's all I have. I have examples of, I don't know if I should show it. And hopefully one day I will finish a real-time procedural demo that I'm making, and there I basically took some of my, as an experiment for now, I took some of my shader toys that I have, like this one here. Let me show you to you. So there is this shader toy that I made as well. It's another, for those in Harvard, this is just a remarched scene, just like the temple we are building, but it's more organic. So I took this guy, baked it in polygons with surface nets, baked some lighting on the vertices, and then in the 3D engine I just rendered it with 32 times multi-sampling, and the same shader that runs in shader toy for the materials, I run it as a fragment shader for the materials of the mesh, and I get exactly the same image running, super multi-sampled beautifully. And I think it was running like 900 FPS on my previous graphics card, which was a 970, I think. So yeah, there are ways to do it. It's not too complex. I think the surface nets technique, I borrowed it from somewhere and I customized it and I improved it and I made my own version of it. But it was like 3 or 4 years ago, and basically it's based on scanning the volume in stacks. So it's like a 3D printer, but kind of the opposite. You have the SDF and you start slice by slice going through points which are regularly spread in space. And for every point you evaluate the SDF, and if it's negative, you start creating a 2D polygon in it, but then you start extruding it up and you start connecting the 2D slices together. Anyway, yes, there are things you can do. OpenVDB, says Garcia del Castillo. Yes, Jose Luis. Yeah, OpenVDB, that's the one, which stands probably for volume description something. I don't know what the B is for, bounding, maybe distance bounds, I don't know. Anyway, let's keep going. We were here, I think. Step number 2. So repetition. Yes, someone was mentioning we are going to be using the mod function to create repetition because we want many columns, and again for the price of one. The idea here is that we don't want to explode memory or complexity in the code. We want to keep things simple and have one single column. So in all we need to do basically is to take the domain where we are representing the column and make it periodic. So let's do it. I'm going to move fast because many of the guys here already know this. We have touched this many times, so I'm going to start accelerating a bit so we can get to the lighting, which is the fun part, I think, for some of the folks here. But let's see how we do this. Okay, let's take x.y, x.x, and I'm going to pass it through a something like that. Okay, so let me explain what I did. Well, first of all, before I even explain it, this is awesome. One line of code, infinitely many columns. The screen doesn't show, but this line of columns goes to infinity and negative infinity, like literally goes to infinity, mathematically infinity. So this is something that in a game engine would be complex to do, or you would have to start adding instancing and scripts and things, and technically inside you would have to be rendering the same thing many times with bounding volumes because you don't want to render them all. You have to do frustum cooling. It gets weird very quickly. Here, just one line of code. So let me explain what it does. It takes the x component, and the mod operation basically is taking x, and whenever it goes beyond 4, which is the second argument here, is whenever the value goes beyond 4, it subtracts 4 from it. So 5 becomes 1. And 5.2 becomes 1.2. And the function as well, if something goes beyond 8, it does subtract 8. So 8.1 becomes 0.1. And the same with 12, it subtracts 12. So every 4 units, it kind of resets the whole number as if it had really started again from 0. So from 0, 1, 2, 3, 4, all is fine, but when it crosses 4, it goes back to 0. So basically what that is doing is, taking the whole space, which is full of coordinates from negative infinity to positive infinity in x, y, and z, and basically focusing only on the 0 to 4 range and repeating it forever. Anything that is bigger than 4 will be as if it had been reinjected at the origin. And that means that because we are describing our column in terms of the coordinates, in terms of the origin of the space, the box was about plus 5 units, but it was like 0 units left and right and 0 units in depth, and the cylinder was centered at the origin. What we are doing is that any point beyond 4, because it gets reinjected at the origin, a new column pops in that new location. So again, if the algorithm is evaluating something at position 12.5, this mode operation makes sure that the algorithm thinks that we are evaluating the function at 0.5, where we do have a column. So a new column shows up in the new location. So there is that. There is the 4.0, which tells us the repetition space. If I made it 7, the columns will be spread apart a bit bigger. But 4.0 is good for this case. And then I have a +2 and a -2 here, which all they are doing is making sure that the repetition range is not from 0 to 4, as I was explaining, but actually from -2 to 2. So 2.1 will be reinjected into -1.9, right? So we are just shifting the region of interest. We are recentering it at 0, which is where we have the column. So there we go, easy. Now we can do the same not only for the x but for the z component, and now we have so many columns that we cannot even see them. Let me move the camera a little bit farther away. Okay, look at that. We have so many columns because now we are repeating it in x and z. So this goes to infinity, only that I have kind of clamped the whole problem to a small area in space, so we can, small volume, so we can render quicker. But yeah, we have so many that that is filling the whole space. So let's fix that. And for this, I have a function that I already prepared that takes the repetition, and instead of making it infinite, it makes sure that we only repeat it a given amount of times. I was saying like 20.1 will become 0.1 again because of the 0 to 4 repetition, but we can clamp that effect to say repeat it 4 times, and from that point on preserve the numbers. So I have that function already coded. I think I called it operation repeat limit, and we pass it the point, we pass it the repetition period, and then we pass it how many times we want to repeat in each coordinate. So something like that. And let me zoom back, and then I can go back to the code to show it to you closer. I don't know, 40. Let's put the camera there. Okay, so again, recap. We are repeating the domain with a spacing of 4, and we are repeating it only 4 times in x and 2 times in y. So we should have, let's see, 1, 2, 3, 4, 1, 2, 3, 4, and the one in the middle. So that's the this is clearly the x component, the x direction, and here in the y we should have 5 copies. I cannot count, but let's see, 1, 2, 3, 4, and 5 columns, and that's the central one, plus 2 to the right, plus 2 to the left, and this is the 2 that is controlling that. If you're curious, I have an article about this in my website, about how this works, but it's based on the mode operation, but then we clamp the effect of it, basically. All right, so what else? Yes, I'm gonna remove the columns in the middle. If you remember the original temple, there are no columns inside, so let's do that. And I'm gonna do another carving operation, pretty much like we did, clamping the column with a top and bottom planes to create a limited cylinder. I'm gonna do the same by carving a box from the inside of the temple to remove all those columns which are inside. And there are probably better ways to do this, but let's do that for now. As the box of P, and I don't know, start putting numbers here and see what happens. That should do it. Let me make it bigger, and maybe let's play. I still see columns inside. 5, okay. Okay, look, we remove the ones in the inside, but I still do see the bases of them. So let's make this higher. 6, and I still have a row of columns here, so I'm gonna make this one bigger. Okay, I'm gonna be adding the floor. So this is a copy of the same. There was another save point that I made for myself in case I would screw up things a lot. But basically it's the same as we had. I think the camera is slightly different and the colors are different too. Actually, you know what? I don't like the colors that much. Let's go back with this one. I think you can see better what's going on. Okay, let's add the floor. If we go to the original one that I made, the floor is made of boxes. So let's go ahead and make boxes. Super easy. We already made boxes, so we know how to make those. I'm gonna call this floor, and we are gonna combine them with a min function, and we are gonna make the floor what is the values I have here? Let me see. Let's make them much smaller. 2 and 2 and 0.1. Okay, it's there in the inside. You know what? Let's very quickly remove the outside so we can see the inside. So that's our tile. I'm gonna make it bigger. Okay, I'm gonna put a scope here, and what about we repeat the domain as well? Where is my repetition domain function that I just used? Okay, here. So I'm gonna take P, actually let's call this one P here, and take 3, Q equals P. Right, that's the same as I had. Alright, so we are gonna repeat this one, how many times? Let's make this one slightly smaller. Okay. Like that. 4.3. Okay, we have a lot of tiles there. I'm gonna make them higher, something like that. Okay, but let's put it back with the thing. Let's push them down. Q is gonna be P, but we are gonna move P down by some amount. I don't know how much. 1 unit. There we go, sorry for that. So we are interested only on the SDFs the SDF values which have a value of 0, and by shifting that condition a little bit to an SDF that is not 0 but 0.3, suddenly we are changing the whole geometry to the next isosurface that is defined by the volumetric function. And these isosurfaces get rounder and rounder the farther away you move from the 0 isosurface. Watch that video, you will see why that is the case. But all we need to do here is to just shift the isosurface a little bit. So this is the repetition operation for those who, I don't know if the screen was not casting the right thing to you. I wasn't broadcasting the right thing when I was talking about that, but this is the repetition function, and this is the box equation. And this is the mean that combines the boxes with the columns. And we take the SDF of the box, and we are going to round it. And all we need to do is, so first of all, yeah, let's subtract an amount from it, 0.1. And that makes it rounder. So now someone was asking in the chat, and this is something I forgot to mention in my previous video, which is rounding shapes makes them also bigger and thicker. Basically, we have a shape at the zero isosurface. By switching to the next isosurface with a subtraction, we are making it bigger and bigger and bigger and bigger and rounder as well. We are inflating it, and it's losing definition, but it's becoming bigger, it's getting volume. So the way to compensate for it is to make the inner box from which we are growing, the rounded box, smaller. So we take the core of the object, the isosurface, we push it inwards, and then by changing the dimensions of the base object, and then we inflate it back by the same amount outwards, and then that rounds the shape. Does it make sense? So you have a box, if you just round it, it becomes bigger, but if you first make it smaller and still make it a box, and then round it, then you can get the same volume that you had, but with rounded corners. So in this case, actually, let me put the numbers here to not make this any more confusing than it needs to be. So this is our box of dimensions 1.9, 0.4, and 1.9. Let's say I want to round them by an amount of 0.2. I subtract 0.2, but I also subtract it from the dimensions themselves. So I make this box smaller by 0.2 units, and then I inflate it back by 0.2 units, and then you get the rounding effect without increase of volume. So look at this. I'm gonna go back and forth. There, 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 and there. So yeah, great. Actually, this is a bit too much, so maybe we can close the gaps a little bit, and this is up to you. And you know what? I think we should round also the base and the bottom of the column, which is here. So we are gonna take that guy and round them a little bit. Ah, no, that's not the one. That's the clipping one. Sorry. This is the... Yeah, let's round it a little bit more. It was already rounded, but like that. Something like that, maybe. Yeah, whatever. That looks good enough. Okay. Okay, there we go. Rounded tiles for the floor. Much better than not rounded. Okay, let's create another layer. So all we need to do now is to create another layer of floor tiles. So I'm gonna copy the whole thing. I'm gonna push them down by some amount. Let's say 7. And now we are going to... Okay, so I want them to be not aligned, but offset from each other. So I'm gonna take the X component of Y and shift it horizontally by half a tile. And a tile right now it's 4 units, right? So let's shift it by 2 units. And that didn't work at all. Oh, it's because I'm using P. So we should be using Q here. There we go. Actually, I'm gonna shift it in Q, in C. Okay, so I just shift it that way. Okay, let me shift it the other way. There we go. So now we have the second set of column of tiles. Let me move the camera a bit away from the thing so I can better see what's going on. By how much? There we go. And also there. Okay. So let me go back to the code, and yeah. So I'm gonna add another parameter here which controls how much I Okay, so it's gonna be this one here, I guess. Yeah, there we go. Okay, so I made another version. I have an overridden. How do you pronounce that? I have a second version of this function, opreplim, which allows me to choose how much the repetition extends, not only in left and right, but left and right individually. So I can repeat something, in this case 3 times to the left and 2 times to the right, and I'm using that to make the whole shape symmetric. So there we go. And also I would like to push it forward like that, so I can also shift in C by 2 units the other way. Okay, Look at that, we have a second layer now. Let's do a third layer, which we don't shift anymore, but we push down by another unit, 8. Now we need to create more repetitions, so 3 and 4, and we need 5 in C. There we go. Okay, that's our base. Pretty. And let's see what time it is, because it is 12:35. We did start at 11:10 or so, so it's been an hour and 20 minutes. I'm going to copy paste a few things now, and with that, then we can move on to lighting, I guess. Okay, let's add the roof quickly. I'm gonna copy paste this, and I think I wrote it down somewhere. Where is it? Let me see. Repetition, columns, the floor. We got all of that done. Okay, the roof. Okay, I'm gonna write here roof, and I'm gonna copy paste the whole block of code here, which is unfair, but there we go. Okay, that's gonna be our roof. It's not connected yet, but so what this is a basically is the equation of a rhombus. You know, we had the equation of a sphere, we made it into the equation of a cylinder, we used the equation of a box. There is an equation of a rhombus, which is kind of you know, like if you take a box from two of the corners and you press in. So the equation is very similar to that of a box. So I guess I just used it in this case. I made it very big and rotated it by 45 degrees to place it at the roof. So nothing too difficult there. I also let me see, the floor, the roof, the noise, let me see. Yeah, and also what we need to do is to add a few more boxes. So before, you know, the gap between the rhombus and the ceiling or the roof and the temple is because I made some space there for putting some of these boxes. Like that, which is again pretty similar to the floor, you know. It's just one box which has been repeated multiple times. And then, just for the sake of adding a bit more detail, I also added a second block of boxes that you can see it on and off here, that kind of complete the cylinder. There we go. Something important that I've not been talking about is that, you know, all these elements have the same colors and materials, and that is not very realistic. So let me switch to a more complete version of this, where of the temple, where every okay, wait, I'm moving a bit too fast, sorry for that. Let me do a few things. So this is the temple that we just made, but if you can see here, every column has a different shade of gray. It has a different color. And that's because I created not only a distance through the distance fields, but every point in space also has a unique identifier, a number that identifies which piece of geometry falls into that point in space. And these numbers are arbitrary numbers, like, you know, the first tile on the floor is number 3, and the next tile is number 20, and the next tile is number 17. It doesn't matter really, but basically the same code that creates the repetition of the domain, you know, the 0 to 4 endless repetition to create an infinite amount of columns. That same code keeps track of which one of those repetitions we are in. You know, the point 8.1 will become 0.1 through the repetition every 4 units, but it will remember, okay, we were in the second repetition. First one being from 0 to 4, the second one, the 0 repetition being the identity, the 0 to 4, the first repetition being 4 to 8, and the second repetition being from 8 to 12. So 8.1 falls in the second repetition, number 2, and you do the same for x, y, and z, and you get, you know, the second repetition in x, and we are also in the third repetition in y, and the first repetition in z, for example. And that gives you a triplet of numbers which you can multiply together and do some operation to it to get a unique number that tells you which overall repetition in space you are. And with that number, you can go back to the code that generates colors and modify or affect the color with that. So yeah, there we go. So you can create individual colors for each piece of geometry. It's not too difficult. Something I also like doing, and that's the thing I commented out here, and I was earlier talking about making things look old and aged and more realistic. That's something you can do in a multitude of ways. In my latest video on YouTube, I talk about one of them, which is modulating the roundness with some random functions. In this case, when I made this one, I didn't think of that technique yet. So I just used a different idea, which is not that good, but it kind of works, which is taking the overall mathematical function of this shape, which is a temple. And now, so you can imagine of this, you know, like a big equation. We had the equation of the cylinder, the arctangent, the sine waves to make the column more detailed. We had boxes, we combined them together with a mean. We repeated the period with a mode function. We combined them again with a mean. We clipped the inside of the columns with a max. All that combined is a huge monster equation. You could write it down, you know, like x squared minus this thing square root divided by, you could write it down. So we take the whole equation and then we add a plus at the end, and then we add some random functions there. And by random functions, I mean something we call noise in computer graphics, which is, you can think of a sine wave, which is still periodic as it goes through zero continuously. It goes up and down, but the height of each one of the valleys and peaks, each one of those oscillations, is random. The height of the oscillation is random. And then there is some constraints about, you know, if you have two oscillations of different sizes, you have to connect them continuously with continuous derivatives and things. So there's some constraints there, but basically a noise function, you can think of it as a randomized sine wave. And actually randomizing sine waves is one way to generate Berlin noise and things like that. Not the ideal one, but it can be used. So that's what I'm going to do here, which is taking all those random sine waves and combining them together and adding it to the monster equation of the temple. And there you can see in the screen, when I enable and disable it, I can create those kind of holes, or I don't know how to call it, like, you know, aging, or it makes the whole thing look older. Like, you can imagine a temple after 2,500 years being exposed to weather and wind and people, then the rocks lose a bit their shape. And yeah, so you can do that a few times. There are some artifacts there. You can see some black pixels. At the time I didn't know how to fix them, so I left them there. These days I could do that without having to have those artifacts. But at this point I would call the modeling done. Again, if the camera was closer to the thing, we would have to add more detail, and I'm not even sure these are correct proportions. But the point is that what did we use? We used one cylinder, two sine waves, one box for the top and the bottom of the column, three boxes only to do the whole floor because we used repetition, two boxes for the ceiling, and one, I think, two rhombus. So we are talking of like 12 primitives, 12 equations involving, what, 12 square roots and a few sine waves. So this is relatively a small amount of computation. If you had this in, in polygons, we would be talking here of, even through instancing, we would be talking of hundreds of thousands, if not hundreds of thousands of vertices, of numbers floating in the memory, plus a lot of processing power in order to consume all that and project it to the screen and light it and whatnot. So this is a bit the power of doing things with maths. And it does have uses in real life, in filmmaking and things like that. I won't spoil a bit that talk that I gave, but basically I guess the one-liner is that when you are thrown to a new challenge, like let's say you are an engineer or a technical artist, which is more what I am, more than an engineer, and there is a new film or a new game or a new whatever that you need to do, and you don't know how to do it because they are asking you to do something difficult. Like we want to render a forest, and we never made a forest before, or our machines, our computers cannot handle more than this amount of geometry, and how are we going to make a forest, or how are we going to make shadows for a character in VR when you only have 11 milliseconds to render and only 3 of them are for the character, and you have challenges like that, and there are no, if it's early in the technological cycle of the technology that you are using, let's say VR, like 4 years ago, or when I was at Pixar, we had very 4 gigabyte machines, and that was what we had at the time in 2010, and they could not render big stuff. So there's a limitation on technology. Then, because the technology cannot give you what you need with standard methods, by using the Mayas and the Unreal engines and whatever, then you have to find solutions which need to be implemented without tools and without the Mayas and the Unreals, and even without pipelines or without the concepts. Maybe using polygons is not the right solution in those super constrained situations. And suddenly, in those situations is when being able to create content just from maths, like skipping or bypassing the technology, let's say, the processes, the bypassing the pipelines and the tools and all those things, going straight from math to pixels, as we are doing here, it's of value, brings a lot of value, because suddenly you can find workarounds and invent or tune techniques that exist without having to be constrained by the processes that are in place, which are insufficient in this case. So there is a very real use of doing things with maths. Not that this is how you want things to be working on the long run, because again, you want artists to be part of the creative process when making a film or a game, and therefore you need to give them tools. But for a moment in time, for a small window of time, when new technologies show up, I think people who can create things with maths have a place and can bring a lot of value and be the first content creators before anyone else can create content, before the Mayas and the Adobes and the Autodesks and the Epics go into the field and start developing tools. Anyway, there's a real use for this, but it is also super cool. It's super fun to do, and that's why I think most people in Shader Toy who are there, right guys, we are there just doing it for the fun, because it's great to, for once, not being the technician who helps artists, but being the artist. It makes, not that this temple is like something you would put in the big screen or in a game, but we can have some joy and pleasure at finding pretty images and so on. Speaking of pretty images, this image right now is pretty ugly. So I'm gonna fast forward a lot and show you this other image instead, which is still not pretty enough, but it is better. It does show the temple that we just had after I added a landscape to it. So I'm at this point when I was making this, so making this temple took me a day, I think. And a day probably is anything from 5 to 10 hours, depending if it was before or after baby. Before baby, my days were 10 hours long. Now they are 5 hours long. So I have been 4 hours in the process or whatever, and I'm here. I have a composition, I have the landscape, I have the temple, I have framed the thing, I have moved the camera a little bit, and I know this is the image I'm going for. And I'm happy with it. I have modeled everything I needed based on this one camera. So I'm not modeling the back side of the temple, I'm not modeling the inside. The terrain is just as simple as it can be to kind of sell the image and give you the sense of perspective and the setting of the picture. But now is the time to make it pretty. And most of the, like 70% of making an image good looking, I think it's lighting. So lighting is the process of, adding the shadows from the right angle, making sure the silhouettes pop, picking the right colors so you have a good color balance, and things like that. So I'm slowly getting better at lighting. I'm still not like super good at it, but what I have learned to do a bit is to avoid ugly images and more than creating pretty ones. So I try things until I detect I'm outside of the ugly spot, kind of thing. So in this case, just by looking at this image, I already noticed right away that I'm not happy. Let me look at the picture a bit. Actually, this one doesn't look bad. Let me see where my lighting is. Yeah, it is not that bad, but I feel that the temple could get some more lighting and I could get more shaping out of it. So I'm going to modify. So I have this sunlight thing here. Let's see where it is defined. So this is the direction of the key light of the sun. Okay, you know what? Let me show you first all the lighting components one by one so we know what we are talking about. So let me remove all lighting. And lighting are equations again. In this case, actually, unlike the modeling process that we went through, which was defining shapes through equations, which is very unconventional and different to how computer graphics is done normally, which is polygons. The equations we use for lighting are similar to the ones used in CG normally. They are not that different, at least not too different to how CG was done 5 to 10 years ago, where colors would be added almost by hand to make the pictures look pretty. And we will see, I still do a lot of painting by hand, as in placing lights in different spots, and we will see that, but the key lighting components are not different to what you would do in a traditional 3D engine, or not too different. So first of all, I always start with the key light. So this is the key light, key because it's key to the look of the image. This is a term borrowed from Hollywood and their, what is it called, like 3-light rigging system, whatever, the 3-point light system, where they would always lead a character first with a strong light from the front to read the face of the character, and then they would put a second ambient light to kind of fill the shadows, and then a third light behind to create a rim or kind of a edge lighting to separate the character or the person from the background. So some of these terms that I'm going to be using are borrowed from that, but basically the key light in this case is the sun. You always need a key light in a scene. Sometimes it can be a lamp if it's an indoors scene, or a fireplace or whatever, but when you are outdoors, the natural key light is the sun, and that's what I have here. And it is coming from a given direction that I chose to kind of give me sad light. I didn't want to lit the temple from the front because it looks very flat. It's like when you take a photograph with a flash and you are lighting your subjects straight from the front, and then you don't have shadows in the scene and everything looks super weird and flat and boring and not interesting. It's always nice to move the light a bit to the side, and in films they normally put it at 45 degrees instead of 0. In this case I pushed it all the way 135, I think, all the way to the back to get long shadows coming to the camera. But that's the key light. There is the ambient light, which is kind of light coming from everywhere. In this case, the ambient light, which fills the shadows. So actually, let me bring back the key light, and all the black spots here will automatically be filled with the ambient light. There we go. And it brings detail to where otherwise wouldn't be any detail. So the ambient light on isolation here is basically a blue light, which is motivated by the fact that the sky is blue, and that's kind of what fills the shadows, the light coming from the sky. It's a lot less intense than the key light. You can see here that The key light is about 5 units in strength. The ambient light is 1 unit, but even less because it's multiplied by little, very small numbers. So probably normally the key light is about 10 times stronger than the ambient light. The key light is yellowish. Here you can see 0.9, 0.55, 0.35. That's a very orange color actually. It's a bit to simulate a sunset. And the ambient light is bluish because the sky is blue. So you get 0.15, 0.25, 0.35. That's RGB. So the good thing of having these two orange and blue colors is that they are complementary to each other. You look in the color wheel, you know, red is in front of green, purple is in front of orange, and blue is in front of yellow. And because they are complementary, we kind of like it. That's what you see in real life as well. If you ever go skiing and you see super white snow, which is the perfect reflector, you will see that the shadows look super blue. So I have that. That's the basics. So this is two lights, and then I have always a backlight, which illuminates a bit from the opposite side of the sun. So the idea here is that, you know, the sun hits surfaces, and the surfaces bounce light back, and the bouncing is going to be, on average, the opposite direction of the light that came to the surface. So if the sun is coming from here, the light will bounce and poof, come back. So if you have a white surface, some light will be reflected and illuminate the things here. You can see this very often if you have, you know, a light source or something, and you have a very saturated color object, like something that is super green or super red. It will create like a red and green halo of colors around it because the light is bouncing. So normally these days you do these things with global illumination and other rendering techniques, but in this case, because it's real time and it's old school, I just put the bounce light by hand, the backlight, and I make it the opposite direction of the sun, and I modulate it with occlusion and a few other things, and then I add some specular. Speaking of occlusion, well, I will touch on occlusion later because I don't compute occlusion. I also paint the occlusion by hand. But basically, yeah, the backlight illuminates slightly a bit more here and makes the thing look great. But going to the key light, I am not super happy with how the temple looks because this area here is super flat. There is nothing of interest here. I have a lot of bright spots here, which is great. It's super aliased, by the way. I will fix that later. And then there is this, which looks great because I can see the landscape, the terrain here with the nice long shadows. But I miss detail here. So I want to leak some light there. So if I go and I search for where the light source is, this is the light direction. This is where I can change where the lighting is coming from. So if I make that negative, you can see that now the lighting is coming from the other side, which doesn't look bad, actually. It looks pretty cool, I think. But let's stay where we were. If I make this negative, I can light it from the front. It looks really ugly because I tweak everything for camera. And this is the problem with making things not physically based, but painterly. You know, like I always treat these things as a painting, not as an engine or a scene that we should navigate. It's more like I'm making a painting, I'm gonna make it look good from this camera. Anyways, just by playing with it, if I make the sun direction a bit higher, then I get this very nice light leaking inside of the temple, and it illuminates some of the silhouettes of the columns, which is great because when they are just flat, it gets a bit difficult to read that these are columns, that they are at different depths, that there is stuff going on in there. It's not a good read of the geometry. But when I put it 0.3 in the y component of the light direction, which means I made the sun a bit higher in the sky, more like it was noon or something, then some of the light is coming through the roof, which has a big hole in it, and it's hitting those columns, and I love it. I love those things. So that's great. The problem with this is that now the background looks really ugly. Like, it's totally bright. We lost the long, beautiful sunset shadows. Not to speak of how bright it is and how much it is competing now with the temple. Like, you know, as I was saying before, if you have 2 seconds to read this image and you're presented with this, your eyes don't know where to focus. Should I focus on the bright spot on the right side of the image? or should I focus on the left side of the image? Because both are super bright, they are calling for attention. So we have to fix that. But again, if I go here, the image is more balanced, but then I lose my beautiful lighting there. So what do we do about this? I'm going to be doing an ugly trick, which, let me see. It's an ugly trick which you should never ever do in a game engine or in a film. And well, not in a film. In a film you can, but not in a game engine, I think. If you do, you will be fired. So don't follow this one advice unless you are in shader toy or making a film, in which case everything is fine. But what we are going to do is to have two suns, one illuminating the temple the way we want, which was by moving the sun a bit up, and another one illuminating the background the way it is now. So we are going to, take the sun direction, which is what we want. I'm gonna normalize it, which we need for the math to work, and that should change nothing. But now here there's a 0.2 factor that we want to use only for the foreground and not for the background. So what we are gonna do is add it and modulate it with a mask, and we are gonna call it, I don't know, sun mask. And now what we need is a signal that, 0 means what we have, 1 means the improved temple lighting. So we need a signal that has value 0 in the background and 1 in the temple. And of course we want to smoothly transition between those two lighting setups, because we don't want to see like a weird lighting seam or anything. We still need the temple to sit properly with the terrain. So we couldn't do something where if terrain use this light, if temple use that lighting, because then in the areas where the terrain and the temple coexist, then things would look weird. Things wouldn't match necessarily, and that can be a problem. So it doesn't have the transition between one lighting setup and the other lighting rig cannot be based on geometry or materials. It has to be a volumetric effect, right? So that's what we are gonna do. So first we are gonna measure how far away we are from the origin, and the temple is centered at the origin. And now we are gonna mask some areas with it. And let me see, that worked, that didn't work, so let's do that. Okay, we got it. So these 30 and 80 values, I remember them, but basically I think the temple is about what was it when we were making the floor tiles? We said repeat it like from -5 to +5, but each tile was 4 units long. So the temple is about like 20 units wide, 20 meters or whatever. So what I said is everything closer to the origin than 30 units, keep it. This is what this smooth step is doing. Anything closer than 30 units, keep the old lighting rig, well, the new one. And anything farther than that, smoothly over the curves of 50 units from 30 to 80, smoothly transition to the old lighting rig. So in this case, basically it's like the sun direction was changing in space. It was a bit like we had some weird relativistic effect where the light bends, but instead of being based on speed or something, it's based on location. It's like, it's like the temple was a black hole or something, and it was bending the light rates in a given direction. And again, if I was seeing this in the wrong context, I would fire myself for doing something like this. But this is the right context. I'm just painting. All these equations that I'm using are brush strokes. They are not meant to be generic code. They are not meant to be reusable. They are not meant to be, something that, anything professional. It's just a painting. I'm making it look good, and the same way in a canvas you would put a color, and if you're not happy, you would go and override it with another color, and you keep putting splashes of color and strokes. That is the same. We go one by one until the image looks good, at which point we publish it in shader toy. Speaking of splashes of color, I'm gonna go for another half an hour, I think. I want to finish something and show you my philosophy when I do lighting. So I showed you one decision I took where, someone is saying there, enter is a flag to amplify the ambient color. Yes, yeah, there are a lot of tricks here. I won't go through those necessarily, but there's one I want to touch, which is, besides fixing the conflict I had with the colors where the background and the foreground were competing, potentially when I was doing the right thing for the temple, and when I wasn't doing the right thing for the temple, the background was gray, but all those things. There's another thing that also pops to me that looks bad here, something that screams for a change, which is the interior of the temple looks too dark and too boring and bad. It's not an inviting picture. Right now, I don't know if it's my screen, could be my screen as well. Everything looks gray and dirty and ugly. In a way, it's not a temple I invited to go in. So I'm gonna fix that by faking some bounce lighting, basically, some indirect lighting. So I'm going to add yet another bounce light here, and I'm gonna make it pretty red. So I'm gonna colorize the inside of the temple. So when choosing a color, you have to think, what would be the color of the bounce light inside of the temple? And you could, write a path tracer and it would figure it out for you, but you can't reason about it. Like if the sun is yellowish and the temple is kind of sand color, which is orange yellow, then the incoming light, which is yellow, will be convolved or multiplied with the color of the temple, which is orange, and that's the color of the resulting light going out. Is orange times yellow, and what that is a super saturated orange or yellow. Yellow times yellow is super yellow, and yellow times orange is a very orange thing, very intense, way more saturated than the source color of the sun, and more saturated than the color of the temple. So I'm gonna use a super saturated orange color. I won't put any blue on it actually, or maybe just a little bit, because you never want blacks in the color. You always want to leak a slightly bit of color everywhere, just in case you need to color correct and bring information, because if you put zeros in a pixel, you cannot do anything with it. Once it's zero, you cannot manipulate it. But if there's a slightly bit of something in there, you can still multiply it by something, by recover some color or some intensity, you can shift it. So it's always good not to put zero, but I'm gonna put something that is almost zero in the blue channel, almost black. And yeah, I'm gonna leave it there. I don't know how intense it should be. I'm gonna make it 3, and then we can make it less. So now I need to create a signal, which is the bounce light. So if I put it everywhere, I get this super orange color everywhere, but this is not what we want. So let me look around to see what I did. I think we are gonna just, the same way I used a volumetric mask to separate the background from the foreground, meaning the landscape from the terrain from the temple. I was using a smooth step to create a signal that smoothly changed from 0 to 1, and that helped me to create a soft select kind of thing. I'm gonna use the same here to select where the orange color goes. So I'm gonna use a smooth step of some values. I think I have some values here. Let's say one on length of pos minus, and here I'm gonna make it 2D as well, and I don't know, I'm gonna put some numbers and then we will find where those are. Okay, let me break it into lines so everyone can see what I'm writing, and we need this thing a bit bigger. Oops, there. Okay, all right, so there you can see I have a blob of orange inside the temple, but it's just at the wrong place, because okay, let me remove it quickly. These patches of light that are coming through the columns and hitting the floor, they would most likely illuminate and bounce back into those columns at the back, not the ones in the front. So we have to move the orange blob, to those columns in the back. And that's gonna be, I don't know, I'm gonna try things until we hit the right spot. Okay, that looks better. Is this what I want though? Yeah. Yeah, 4 maybe. 5 is good. 5, 5, and something like that. Okay. Okay. That is clearly too much though. Like we would never have that amount of illumination, but we are in the right spot. Something we can do, first of all, before lowering down. Well, actually, you know what? Let's make it smaller so we don't. So it looks a bit better. Okay. That might be a bit too much. 0.5. Okay, maybe 0.6. And this is where your eye has to play a role at picking the right numbers. Okay. Yeah, look at that. Also, actually, let's make the signal 0 and disable the bounce light back there. Okay. Boring. Somehow better. Boring. Somehow better. Still looks like too uniform. So now I would start doing things where not necessarily physically based or physically inspired even. I would just start adding variations to that lighting by using whatever. I think one of my favorites is just to use the Y component, you know, of the normal. We could be using the X component. Actually, let's use the X component just because. And maybe negative. Okay, so I'm modulating the amount of lighting by the normal, just because in real life you would expect different orientations of the surfaces to pick up different amounts of lighting. And since we don't really have a light source, I mean, we could actually, you know, decide that the bounce light source is down there on the floor in the center of the temple, down where the light of patches are. We could do the average of that location and consider that to be in the source of the light, of the bounce light, and that's how actually old school virtual point lights would work in order to fake global illumination. And then with that light source we could compute the dot product of the normal to that light source direction and do some stuff. But you know, this is a quick drawing, a quick painting. Anything is okay. So in this case I'm happy with that. And yeah, I mean, the original shader that I made has a better lighting than that. It has a more better looking colors and stuff, but this shows the point where I just created basically, you can think of this blob of color that I did like a volumetric brush, where, you know, there was a painting I didn't like and I took my brush and put there a blob of color to make the thing look better, and it's done. It's just a smooth step and a square root. Like, it costs nothing. Okay, other things we can do is add some, you know, like overexpose the image a little bit on the right side, because the sun is coming from there and those pixels on the right are super bright. So you could expect that the film is a bit overexposed there, and that there is a bit of brightness in the image in that area. So that's something I do a lot, and all that you need to do basically is just to measure you know, how far the view direction for that one pixel is compared to the sun direction. And what did we call the sun? We called it sunlight. Oh wow, okay, that's too much. So we shape it a little bit again by raising it to a power, maybe 8. And you know, this is giving us an indication that the sun is around that area. So now we can take that, and again, the POW function, just like in the sine wave, makes things, in the sine wave, the POW function was helping us make things spikier. In this case as well, we can take this signal that indicates it's brighter the closer we are looking at the sun. We can take that and sharpen it a bit with the POW function by making it, raising it to a high power, like 8. And then we can, you know, we make it a bit orange because the sun is kind of orangey. and then we lower a bit the intensity, something like that. And now that I see it, I want it wider actually, so power 4, but now I lower it again in amplitude, something like that. And now I think it's too much, so instead of 4 we did 6. 8 wasn't enough, 4 is too much, so we make it 6. This is kind of a binary search, and there we go. On, off, on, off. Great. The next thing would be to convey the sunset, quality or nature of this scene by making a red horizon. And let's see, this is the sky here. Well, you know what, because we don't have that much time, I'm going to go to the final image and do it there. It doesn't make sense for me to copy and paste too much when the code is here. So this is the final shader, which also have some reprojection based anti-aliasing, which is a very technical thing that helps basically smooth out the pixels and blur the image a little bit in a meaningful way, not just blurring everything, but really blurring in a geometry aware way, so you can soften the edges and anti-aliasing. It's actually super sampling. But where is my sky? Sky color here. So actually let's look at the sky step by step. So this is what we had. So that's the sky. It's blue, as you can see. The first thing I did was to add some clouds, or a hint of clouds. That's done by ray tracing a plane which is high in the sky, and then texturing with some noise. In this case I'm using just a texture. Normally I would create a mathematical cloud, but in this case I was moving quick in the creation of this picture when I made it. And yeah, 2017, I definitely had a baby then, so I just used a texture just to make my life easier. And yeah, so then the next thing is adding the sunset. So this is just a vertical gradient, which I normally use to create the horizon, but then the closer you are to the sun direction, the longer the gradient becomes. So I think I'm using an exponential to make the you can see, okay, if you look at this line of code, you can see there the sky is just blue in the background, and then I have this line which mixes the blue with some level of gray based on this exponential of the y component of the right direction. Meaning, the closer, the more horizontal the ray is, the more horizontal a pixel is, or the closer the pixel is to the horizon, the closer to 0 the y component of the ray is, the bigger the exponential becomes, because exponential of negative x is highest at x equals 0. And then the more we are going to be blending the original sky color with this other white color. Normally the sky horizon is brighter than the sky, and it's also more desaturated, so it becomes very desaturated blue, if not gray. You can look at real pictures and you will notice that. So that's fine, and that creates that horizon. But then I use the same to inject some red color, but the fall off of the exponential, which is 30 for the background, when it comes to the red color, I make that fall off smaller when the ray is closer to the sun. So I also measure, I again measure the distance of the ray or the pixel to the sun with a dot product. I take that and I use that to decrease the fall off of the exponential. And that naturally makes the horizon color gradient to go from thin to thick again, and then thin again as you move away from the sun. So that creates a nice horizon. Similarly, those colors have to, those background colors for the sky have to match the fog color. So let me show you. This is what the, this is what the landscape looks without fog. Fog is, or haze is just the phenomenon where the farther away something is, not only the smaller it is, which helps you understand depth, but also the blurrier or the fuzzier it is in colors, at least on planet Earth, where, because there is, air and oxygen and molecules in the air, the farther away something is, the more of those molecules there are between your eye and the object, and the more the light from the sky and the sun are going to be bouncing around those particles and scattering light, and basically the farther away, the more light the air catches. That's how I see it. The air is transparent, but it's not completely transparent, just like water. When you go underwater, things which are far away, they get, blurry, and they lose contrast, and you don't get to see much. So it's the same for the air. It just happens that the air is thinner than the water, and it takes a longer distance to make the colors blurry. But the effect happens, and there are two effects happening. One is extinction, and the other one is in scattering. These are physical terms for how light behaves, but basically the more molecules there are between you and something, the less light will make it to your eye from that something, because that light is hitting more and more particles, and this becomes like small shadow casters. So there's an extinction factor, which is this one here, that I can show you the difference on and off. It multiplies, basically just fades things to black because there's less light coming, and then I inject light back through the in scattering, which injects normally blue color, which is the scattered color of the sky. And that blue color, and this is the point I wanted to make, has to be in sync with the background color of the sky, so both blend together. And the same way the sky color gets more red the closer a pixel is to the sun, the fog color also gets more red the closer the pixel is to the sun. So instead of using just a constant blue color for the fog, always a good idea to colorize it. And I think that's it. I think that completes the thing. Oh, maybe just a bonus for whoever is left, 20 people still, good. Let me show you how I painted occlusion. Occlusion is always one of those things that still tricky, but it's very important. So let me remove all, all the post-processing and everything, and just for the sake of let's make the sky white. All right, so this is our occlusion pass. This is what we use for modulating all the lights except for the key light. Very important, don't do that mistake. I have seen people, especially people in the WebGL community who are not that much into rendering, and usually copy paste shaders and from other places, and I have seen a lot of people there doing, multiplying the key light in their PBR shaders with occlusion, and that is wrong, because the sun, the key light, basically the direct lighting, right? The direct lighting component before things bounce around of the key light, which is a punctual light source, a small disk of a light source. Maybe it's a half a degree of a cone of light in the sky. That's the sun or the moon. Then basically that thing is in shadow or it's not. You just cast a shadow ray or a few if you want to have soft shadows, or you do a shadow map, and the key light is in shadow or it is not. But occlusion is measuring something different. Occlusion is measuring the average exposure of a surface to the sky. So don't use the occlusion to modulate the key light, because it doesn't make sense, and all it does is to create a very unrealistic and cartoony and old video gamey look to your scene. And in the old days, sometimes they had to do that because the lighting was computed in one pass, and then the ambient occlusion or the screen space ambient occlusion was computed in a different pass. And once you have both informations, the whole light buffer and the occlusion pass, by then you already had lost the information of the different light components. You only had the accumulated lighting of the scene, including the key light. So all you could do is to multiply both and hope for the best. But it wasn't a good idea, because you were effectively multiplying the key light with occlusion, which is bad. These days you can do differently. So occlusion. So I was saying the occlusion, which is this signal you are seeing, as you can see, modulates all the signals or the lighting components, because I'm faking global illumination, and all these lights, except for the key light, are capturing or mimicking or emulating bounce lights that come from everywhere, kind of, but not the key light. The key light doesn't take the occlusion signal, but everything else is the backlight, the bounce light, and the ambient light. And this is wrong, of course, because the ambient light is the sky. Well, the ambient light actually is the one that makes more sense to use occlusion. But for the backlight and the bounce light, Ideally, you should be casting shadow rays in the direction on the cone where the bounce light is coming from, but occlusion, since we already have it computed, we can reuse it and kind of mimics a little bit what we are trying to do. And if we do remove it, then the backlight looks very flat for sure. As long as we do the right thing for the key light, which brings 80% of the lighting information, as we said, is 10 times stronger than the ambient lights. At least we are doing 80% the right thing. And if the other 20% we are doing the wrong thing, but it helps to make it look better, then it's 20% bad only. So let's look at that occlusion signal, because it is less straightforward than you might think. It's not just computed by the usual SDF trick, where you measure a few SDF samples around the pixel that you are shading, and then you kind of compare how far the objects are according to that SDF measure compared to how far you actually placed the sampling point from the surface, and then you look at that discrepancy, and from there you derive an estimation of how concave or convex your pixel is. So instead of all of that is going on as well, but that's not enough. So this is what you get when you do that. Let me show you. You get that. So this is what you do with the cheap and well-known now SDF ambient occlusion approximation. And it is okay. It does bring some detail. It captures some nice details on the terrain. It captures the contact between the tiles on the floor and the columns, and the base of the columns with the body of the columns, and even the internal, the little cracks that we carved inside the column to fake the stacking of bricks. So all that gets captured, and also it captures the concavity in the ceiling, where we have that triangle that is carved from the base shape, but it is not enough, especially because it's not long enough. The sampling of the SDF is not big enough to capture all the occlusion that would happen inside of the temple due to the columns that are there. So I would expect the inside of the temple to be pretty dark in terms of occlusion. And if I change the code that is computing this occlusion to make it wider, then I lose the small details. And then I could have two occlusions and multiply them together or do a mean function, but then I'm paying twice the cost and the compilation time probably. So not a good idea. But something I do a lot, and I did use this in films, and is that because I'm in control of these shapes, I made them, I can create an occlusion signal that matches the geometry properly. And let me show you. This is the FOC, stands for fake occlusion. This is the occlusion signal that I'm creating by hand to complement the computed ambient occlusion approximation. It's all approximations of approximations, but thanks to this extra occlusion, I get that extra darkening in the inside of the temple. I get some extra darkening in the inside of the triangle here. I get extra darkening here. I don't know if you can see this small gradient of color here, where the top part of these bricks, because they are closest to the ceiling, they get darker. And also the interior of the columns, the parts of the column that are facing inwards, are darker than those which are facing outwards. So all those signals, that fake occlusion is made by hand, and when multiplied by the computed occlusion, it brings the kind of, puts it all together. It kind of makes the occlusion good enough to be a good source of modulation for the backlight, ambient light, and the other bounce lights. So how that one is done, the fake occlusion, let me see, it's pretty much painted by hand. I do start with a fake occlusion of 1, meaning white, meaning don't modify the computed occlusion, and then I'm going to start adding terms where I make that signal darker and darker according to different criteria. So for example, where is my, I think this is my architecture, isn't it? Yeah, okay, let's start looking. Yeah, so this one, HO, that's the one I don't know why I call it HO, to be honest. At the time it made sense for me, probably. Maybe horizontal occlusion. I think that's what it is, horizontal occlusion, clearly. Still remember, 2 years after. So that basically is doing what I was saying. It's measuring the angle between the surface normal of the temple, comparing to the vector that goes from the point that is being shaded to the center of the temple. Basically it's like, you can think of it as having a negative light, a light that sucks light, that is placed at the center of the temple. So, if you had a positive light source, if you had a normal light source in the middle of the center, all the parts of the temple which are facing the light, which are facing the inside, would get brighter. In this case, they get darker. So all that is going on is a dot product, I guess, between the normal, but I'm only considering the X and C components, just the horizontal. It's like we had a two-dimensional world, and I'm doing lighting in a 2D world. So that's why horizontal occlusion, I guess. And then I'm doing the normal dot product, and then I'm adding nor.y times nor.y. Probably this is to bend a bit the light source to the bottom and the top. I don't know. At the time, it made sense to me. So that's the first component, and as you can see, that helps take the columns, which otherwise would be super bright in the inside, and make sure that everything that is facing inside is darker, while the things which are facing the exterior are still as bright as they were before. There's another signal here, which is measuring, that is the dark blob for the floor. So the floor also needs to get darker in the center, because again, the more in the center you are of the temple, the more columns you have around versus the parts on the outside. So all I did is just to create an ellipsoid. I take the length of the position of that pixel. I am multiplying it by these amounts here to make it an ellipsoid. I'm stretching it twice in the X component and 4 times in the C component. That's the 0.5, and you could think of this as 1/2 and 1/4. So I'm stretching the measurement by 2 and by 4 in X and Y, X and C, or Y in this case, and using a smooth step to again create a selection mask, and then I'm biasing it by 0.4. Probably we could do 0.2 and get more dark inside. There we go, it's darker now, and maybe we could even stretch it a bit farther and make it look better. I don't know, up to date. Probably I didn't spend too much time, but look, with and without, I think it helps a lot. And then I have 2 other modulations here. Let's see what they are. I think they are related to vertical gradients, probably. Yes, so this is without. When I add this one, I don't know if you can see the difference in the columns. On the top of the columns, they get darker. And that's to simulate the fact that the center of the column and the base, they are very well exposed to the environment, right? Therefore catching a lot of light, probably, not very occluded. But the closer we are to the ceiling, the more percentage of the view the ceiling takes. And therefore the more occlusion you will have in those areas. So the higher you go in the columns, the darker they should be. And this is what this vertical gradient is doing. And all it is a smooth step of the position minus some number and bracketed between 2 some numbers. So this controls how wide the transition band is, and the 3.4 computes how high the ramp starts, where it starts. And again, the 0.4 and 0.6 just are biased to control the contrast, so I can make it more contrasty, like that, and maybe lower it a bit, like that. Maybe it looks better. I don't know. Maybe that's too much occlusion. 0.5 and 0.5. Anyway, you can see that I just painted the occlusion vertically. And this one over here is probably doing the same. Yeah, it's doing the same for this area where this part of the ceiling, because it's coming out, it will probably occlude part of the lighting coming to those points down there. So that there's another ramp there that is also done with a smooth step, very, very similarly. It's at a higher altitude because this thing is higher, and it's a shorter ramp. It's a smaller, it's a shorter or more sharp transition. So basically, that is painting the occlusion for the temple, and as you can see, it's very manual. The same way I painted the indirect light by hand by putting a blob, I painted the occlusion by hand, or some of it, to create extra detail. So that's it. This is the final picture with all the elements in place, carefully placed with a lot of love for a whole day. And we didn't talk about the terrain, but yeah, there is some color gradients there, and the foam, which are all tricks, of course, the different shades of blue. But I think that's it. I don't know if I had anything else. I'm gonna open, I forgot to do Q&As. Let's do one Q&A before we call it a day, and see if people have any questions. I think I've been streaming. Okay, I'm always terrified that I haven't been streaming for an hour or something. Okay, let's see if people want to ask any questions. Where's my OBS? Here. All right, let's see. If not, I will drink some water. Minu Young, I guess this is from Korea, or maybe China. I think it's Korea, right? Could you cover the AA, anti-aliasing? Yes, I can. What caused the black dots glitches? What could fix it? Okay, so there are a few questions. So much effort. Yes, it is a lot of effort. But it's fun. And I think it's worth it. I enjoy, and sometimes we invent little techniques, right? So that's great. Anti-aliasing. Yeah, so anti-aliasing is a super simplified version of temporal anti-aliasing, which is this technique that became popular 3 years ago, I think. Because the Unreal Engine started using it, and then also a few other games used it, which is based on the idea that, one way to help but not fix anti-aliasing is to supersample, which means to consider a pixel not a point at which you inject a color, but an area, and therefore that area in the screen, when receiving information from the 3D scene, will receive information in all the area, not just in a given point within the pixel. What that means basically is that computing lighting becomes an integral, and rasterization becomes an integral, and one way to simulate all those integrals and kind of approximate an area with current rendering techniques is just to have more pixels, or have subpixel if you want. So you could think of it as rendering in very high resolution and downsample it, or just having many subpixels. Now, doing that is expensive because there's more memory, more depth buffer that you have to keep in memory, more color buffer, more bandwidth that you are using. And the GPUs, if anything, are good at computations, but not so much as to add bandwidth and reading memory. So it gets expensive very quickly. So that's why games cannot afford it if they want to keep a 60 FPS frame rate. So one way to do it is multi-sampling, which I won't cover it, which is doing super sampling only for the depth and not for the color. But another technique that they invented at Epic was to kind of reuse the rendering that you did in the previous frame of the animation and consider that information as valid information for the current frame. So what you are doing is every frame you jitter a little bit your sampling points. Basically, the pixels move a little bit by half a pixel every frame. And if the camera wasn't moving and you were taking all those frames that you are jittering and just accumulating them over time, you would get, after some amount of time, you would get an image that is equivalent to super sampling. But when the camera is moving, that becomes a problem because the jittering basically doesn't guarantee that the thing you are sampling is the same thing you were sampling the previous frame, especially if the camera is moving fast or the object is close to camera. So what this temporal anti-aliasing technique is doing is still do it, still reuse the pixels from the previous frame, but look up where that pixel what the current pixel was in the previous frame. It's a bit similar to what video codecs do, where they want to compress color by taking differences across frames to encode only the deltas, but they need to know where the pixel was in the previous frame. So they extract motion vectors and things. The good thing is that in games, you don't need to extract motion vectors like video codecs do. You can generate them on the fly from the same vertex shader that rasterizes the geometry. So basically, you render a velocity vector field, and then you use that to reproject the current pixel in the previous frame, pick the color from there, and accumulate it on the current pixel. However, in this case, because the objects don't move, and all the movement in the image is due to the camera movement, I don't even need to compute velocity vectors, because I can simply transform the pixels with the camera matrix of the previous frame and transform it again with the current camera frame and take the difference. And that gives me a velocity vector on the fly, on the spot, without having to accumulate or store velocity vectors. So this is what is done at the very end. So this is the shader, the main shader. This is where we saw, this is where our lighting is, our gamma correction, our color processing. And normally this is where you would just do, frac color equals call. And that would be end of the shader, end. But instead, this is the reprojection technique where I fetch the old camera matrix, and I can explain how I do that, but I extract the old camera matrix from the previous frame, and then I use that to generate I take the point that we intersected in that one pixel, so we have the ray marched, found an intersection, that's a point in space. I take that point, I project it back, I converted it to camera space through the camera matrix. This is this line here, camera space. Then I project it to NDC, or normalized device coordinates, which is your traditional -1 to 1 coordinate system in 2D, by doing the perspective division, which is how GPUs would do it as well. I convert to screen space or viewport space by normalizing from 0 to 1. I undo the dither, which is a technical thing, but basically then I go to raster space, which is texture space from the previous, the texture that holds the previous frame, and then I sample it. And I sample it here. That's our color, and then basically down here I do the accumulation. I blend the current color with the color we read from the previous frame. And yeah, there's some trick here where I make sure that I don't blend across objects. So I take the depth buffer, which I also stored in the previous frame in the same texture as I stored the colors. Take the depth, I compare it to the depth of the current pixel in the current frame, and if that's too big, if there's a big gap in depth between the pixel and what was at that pixel before, then it means that probably these two pieces of information belong to different objects, and then I don't blend. But that's pretty much what it is. And then the trick to read from the previous matrix, to read the previous matrix, the previous camera matrix, is I store the matrix, the 4x4 values, the 16 values in 4 pixels in the color buffer. So if you look down here, I don't know if this will make it through the streaming technique, through the MP4 and all that, but here in the very bottom left corner, you should be able to see a very bright pixel. And that's because those 4 pixels down there are storing the coordinates of the camera. So that's why down here I make sure that if we are in the first row of the pixels and first 4 columns, then I store the camera matrix in those 4 pixels. So that's how it works. The terrain, can you cover it shortly? Yes. Well, there was something you said that now you could avoid the artifacts from the FBM on the column distances. How would you do it now? I would do it differently. I wouldn't just add noise to the whole thing. Well, I think those black pixels are due to 2 issues. One is the fact that I wasn't using always the correct clamped repetition function. You know how I use repetition, but then I made a function that clamps the repetition so it doesn't happen forever. In some of those floor tiles, I actually did have an infinite repetition, which then I clipped with a max function. And that creates problems on the edges. And those problems chained with the natural problems of displacement in SDFs creates the problem, I think. So I think that just by using the right repetition function, I could get rid of many of those problems. Still, if I had any due to the FBM, then I would use the technique which I explained in the latest video on YouTube, which is modulating the curvature of the rounding, modulating the rounding of the boxes instead of blindly displacing the whole surface up and down. That would create a very nice look. And if that still didn't fix it, and I really wanted those bumps inside of the tiles, I think I would do some more constrained thing where I remarch the whole thing without displacement, and then based on the material I add another layer of displacement or something. I don't know. I would have to be willing to do it and try, but I think I know a lot more things now that I did back then 2 years ago, and I think I should be able to have a clean, pretty image without artifacts. And maybe I will do it. Sometimes it's not rare for me to revisit shaders that I wrote 3-4 years ago and tweak them again and fix things and improve things. I've done it quite a bit, so it's funny because sometimes I see people copying my shaders and they show up in Unity plugins and in places like that. And when I see them, I can't tell when they copied it because some of them don't have the latest fixes that I did for the shader in Shader Toy. So maybe one day I will revisit this one. But yeah, I'm confident I should be able to create a clean image for this one at this point. Yeah, you're welcome, Minu Young. Can you cover the terrain? Yes, the terrain, this one doesn't have much. Actually, normally, as I said, I would create a procedural terrain with noise and FBMs and a few other techniques. But in this case, I believe it's straight texture. I think the displacement, the height map itself of the terrain is just, yeah, here we go, terrain. Let's look it up. If I remember well, it's just, yeah, it's texture samples. So, well, first of all, oh, where is it? I lost it again. Sorry for all this. Okay, so first of all, this terrain is a height map, which means the SDF, it is not correct. And actually just a week ago, while I was at SIGGRAPH Asia, I played with some techniques that allowed me to do a terrain, which is an SDF, which is a true Sine distance field or a bound to it, which means you can remarch it without artifacts like any other SDF, like a sphere. And the shader is there online. It didn't end up looking very good, but the basics are there. You can look it up. It's my latest shader in Shader Toy. However, this is not that. This is just a plane, the distance to a plane, and then that gets shifted up and down with a height map, which means you get the wrong SDF, especially if the terrain is very steep. If you have high slopes, big slopes, then the SDF is very broken, and that's why down here, somewhere, I'm taking the SDF of the terrain and then multiplying it by 0.35. So I'm slowing down the remarcher potentially in those areas by a third, just because my SDF is not correct. I'm sure if I remove it, I will have artifacts. Otherwise, I wouldn't have put it there. Let's see. Yeah, it doesn't look that bad actually. But yeah, it's just a displacement. So in this case, the displacement is, let's see, it's made of layers. Let's explore what I did. I forgot what I did. So the first thing is a base layer of height, which is based on channel number 2, which is this texture. So I'm using this texture as a base elevation map. You might notice this says texture good instead of texture. So I could use just texture, the normal, the normal texture mapping of the GPU. And then you can see there are these artifacts. You can see squares. You can see these very flat polygons kind of thing. And that's because the hardware is using bilinear filtering to sample the texture, which means the landscape you are generating is just made of bilinear patches. And there is a discontinuity between the texels. So I did write this other function, texture good, which I wrote, and it's up here. And it is smoothing out the bilinear nature. So it's not jumping to bicubic interpolation, still bilinear in that only 4 samples are taken, as you can see here. But I do disable texture filtering by fetching always from what is it? Oh, from fetching always from the MIP level 0 by using texture LOD. And then when I have those 4 samples sampled without any interpolation, I do my own bilinear interpolation by using a cubic interpolant. It's kind of a smooth step function, which is this one, line 148. So basically, instead of linearly transitioning from one color to another color for a given edge of the patch, it kind of stays for a longer time with the first color before very rapidly transitioning to the second color, and then taking a long time before staying on the last color. So basically, it's kind of a smoothing of a bilinear interpolation, and I have an article that talks about that. I think it's called Better Texturing. If you go to my website, which is here, articles. Isn't it called? It's somewhere here. Interpolation, maybe. No. Yeah, improved hardware interpolation, maybe. No, it is not that one. Okay, I should do a better job naming my articles, but there is an article here that talks about this exact issue. But basically, yeah, it does that, and if I bring it back, you can see that now the polygon shapes are gone, so that's great. And where is my terrain? Here, terrain. So that's the first layer. Let's see what the second layer does. Oh yeah, this is important. So the second layer is the hill. So no, hill, and that's done just by, I place the terrain really low, and then I sculpted the hill up by using a smooth step. So the closer you are to the origin in terms of x and c in 2D, because the temple is centered at the origin, the closer you are to the temple, basically, the more I push the terrain up, and I just do it by just by mixing the current altitude to an altitude of -7, which is where the base of the temple is, and the blending between the original terrain and this bump, which is a cubic function, which is a smooth step, is based on the smooth step. Yeah. Then there's a third layer, which is adding a higher frequency. Again, I use the same texture, channel number 2, with a higher frequency. So this was divided by 10,000. As you can see here, 0.001, that's the coordinates divided by 10,000. Here I'm dividing it by 5,000, I think, or 500 or something. It's a higher frequency version of the terrain, again, added to itself with a smaller amplitude. So the first base layer is creating variations of, from 0 to 90 meters. And the second layer is adding details of 7 meters height. So it's a lot less detailed. And this is how nature works, right? Like, the more detailed structures you have, the smaller they are as well. So that's the principle of FBMs and fractional Brownian motions and terrains and things like that. And then the last one, I am adding yet one more layer of high frequency detail. Should be noise, but instead of noise, I think I just use texture 0 to give it more structure. So it's again even higher frequency, and it has smaller amplitude. So it's again the same principle. Big things give you the overall shape, higher frequency, which means smaller wavelength, and smaller amplitude add more detail, and even smaller wavelength and smaller amplitude populate the thing with even more detail. So the last one I didn't even bother to do the smooth filtering. I just went straight to no filtering at all, actually. Well, just bilinear filtering. Yeah, that's it. What is the USD box used for in modeling the roof? Oh, so USD box stands for unsigned. Okay, that's funny because SD stands for signed distance to a box, and the U is meant to be unsigned, but I didn't remove the S, so it should have been UD, unsigned distance, but it's USD box. Maybe Yeah, I don't know. What is it used for? Let me see. It's probably to kind of clip the roof. I guess we are talking of line 246. Well, let's see. Yeah, I think it's clipping. So the rhombus, the SD rhombus, which is the rhombus side that makes the triangle shape in the roof, is just a 2D shape, which has been extruded to infinity. And again, in my website, I explain how to extrude things 2D shapes to a limited amount. I call it elongation, and there is an article about that and a few shaders. And that creates a very good SDF. This thing that I'm doing here with USD box in line 246 is a bad practice. Don't do it. But it was probably the fastest thing to get me going again. I had one day to do it, so it was running. But basically it's taking the 2D shape, which otherwise it's infinitely big, and chopping it and clipping it to a given region to make sure it doesn't extend forever and stays within the boundaries of the temple. So that's all it is doing. And it's unsigned because the implementation of a unsigned distance to a box, meaning the distance to a box which just returns zeros inside of the box instead of negative values, is a bit cheaper, like more efficient to compute. It can escape a few max operations. We can check it out. Where is it? Rhombus. Okay, here we go. So you can see that the USD box is like SD box. It has this part here, but it doesn't have all this min and max part, which means it's unaware of negative distances in the interior. But for some operation, that's fine. And in this case, it was. Actually, if I were to review this shader, as I was saying before, and fix some of the black glitches, I would also fix that. I'm going to write it down actually for myself. I'm going to put something to do, fix black glitches, fix USD box of rhombus with elongation operation. So yeah. Is there a way to add global illumination in ray marching? Yeah. There is. I think there are a few shaders doing it in ShaderToy. I mean, ray marching and global illumination are orthogonal concepts, meaning that they don't limit or affect each other. So yes. So basically, ray marching, if anything, is a substitute for raycasting. Raycasting being the core operation in a ray tracer. So ray tracing is the idea of casting rays in space, as you know, and following the light sources and shadows. And the basic operation, the primitive operation, is the intersector. That's a raycast operation. Some people think raycast is just when you do it in 2D, like in a Doom game, but raycast in general is casting a ray in space and finding an intersection. That you normally do when you have triangles. You can do that by traversing a KD tree or a BVH or something, and there is all these technologies. And ray marching is a substitute for that, so that you can ray march objects which are described not through polygons, but through mathematical equations. That's all ray marching is. From that point on, and we didn't show it, but that's just a for loop that slowly marches through space, therefore ray marching, until the intersection is found. And that's all it is. At that point, that's the inner core of the ray tracer. Anything that happens in the outer shells of the renderer is independent. So you could have a ray tracer implemented with ray marching inside, or you could have a ray tracer with normal raycast implementations. You could have a path tracer with normal raycast operations, which is what most people do, or you could have a path tracer with an inner ray marching core. And once you have intersections, you could do your regular light sampling, Russian roulettes, Monte Carlo integration, your multiple importance sampling, all those things with ray matching, no problem. And I have a few images of my own that I have done with ray path tracing here, and I have probably not the best because it's not like I use it so much, but if I go to basic Monte Carlo, this thing here is ray marched global illumination. It doesn't have specular reflection, so it doesn't look very realistic, but you can see bounce lighting and things which were not painted by me by hand. This is coming from a path tracer. If the terrain is a height map, where does its color come from? Colors of the terrain are probably very simple. Probably is just a brown mixed with green based on height or slope. Let me check. Let me close all of this and let's check it out right away. Okay, so this is the terrain, I think. Yeah, so there is a brown base layer. Let's show that first. Actually, you know what? Let me multiply this by something low so we can see it. Okay, there we go. So it's a brown layer, nothing on it, nothing special, just, well, sorry, I'm lying. This would be a constant brown color. And actually we should multiply it by, sorry. Okay, this is our base color. It's kind of pretty white from what I see. 95, 9, 85. Just a constant color. Then I multiply it with a texture, which is texture number 0, which is this thing here. And I guess I use that to bring a bit of color variation. So you can see now there are some darker browns versus lighter ones, or grays, I would say. Just to bring a bit of color variation on the base layer. And it's always about layering detail, just like in modeling. So the next thing here is the shoreline wet rock line. You will see what I mean. You see that line that showed up where the terrain contacts the water? So it's gone, it's back. So that's to trick the brain into thinking that those rocks, because of the tides, you know, high tide and low tide, those rocks are sometimes underwater, and therefore they grow different type of vegetation, and maybe they have mussels and shells in them, and they are wet and they are darker. So just a line, which I just take the, you know, the height of the pixel in world space, in world coordinates, and the closer it is to the sea level, the darker I make the pixel. So that's what it is going on here. It's a smooth step, you know, so the sea level is at negative 25 meters. And for about 1 meter, from negative 25 to negative 24, all that area is going to be darkened by 0.25. So everything above is going to be left unchanged, and everything below that line, 1 meter line, is going to be multiplied by 1/4, making it darker. So that helps sell the idea that there's a different material there. And then what else is going on? There's a bump map to bring some extra detail, which I think we could do without, to be honest. And then there is the grass layer, which, yeah, normally the grass layers are based on the slope. So you can see the green there showing up. No green, green. So basically, as soon as the normal of the surface of the terrain is facing up, meaning we are in a kind of horizontal surface, we tint in green to get grass. The idea is that grass doesn't grow in areas which are very sloped, like cliffs and things like that. And that gives a very nice look. The other thing, important thing, is that I also remove specular contributions where the grass is. So normally rocks are shinier than the grass. The grass is more, you know, it has back scattering, and it's the blades of grass are facing random directions as well, and that kind of diffuses the specular reflection. So normally, not only I tint in green, I also reduce the specularity, and that's it. And just, you know, like three, like base color times a texture, dark line next to the ocean, grass when it's facing up, which is just green, and that makes it. There's a lot of trick in the brain into thinking that there are more things than there are. And that's something that we use a lot in films as well. It's about tricking the brain more than trying to be photoreal or realistic or adding complex rules to grow grass based on algorithms and things. Just put green and it works. Paulo Falcao says, thank you, man. Yeah, he says he learns a lot every time he watches one of these videos. Thank you. I love your shaders. You're one of the very first shader toy users as well. I remember your shader with the black and white spheres. Okay, guys, thank you so much. Thanks for being here. It's been fun. See ya.